Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to take a second and just imagine looking through a viewing portal, but you're not looking at the universe as it is today. You are watching a mirror image of our very own solar system, but at the exact moment of its chaotic, violent birth.
Right.
You're not seeing Earth and Mars and Jupiter all neatly sorted into their stable orbits.
Yeah.
You are watching this swirling, turbulent delivery room of a cosmic neighborhood. And the craziest part is, you are watching it actively unfold right this second.
Yeah, and for the vast majority of astronomical history, trying to understand how planets formed was basically an exercise in forensics.
Right, like a crime scene.
Exactly. I mean, we had our own mature solar system to study, and we were essentially just investigating the aftermath of a massive explosion.
Just looking at the debris.
Right. We had to look at this cold debris, the current orbits of the planets, the makeup of asteroids, where the comets are distributed. And from that, we had to try and reverse engineer the exact placement and the yield of the original dynamite.
Which sounds impossible.
It's incredibly difficult. I mean, we had theoretical physics models running on supercomputers, sure, but we lacked the direct observational evidence of the process actually occurring. But now, well, the paradigm has completely shifted. What's fascinating here is we are transitioning from guessing how planets form to actively watching it happen. We basically have a camera recording the blast.
Okay, let's unpack this, because that shift is exactly what makes late March of 2026 such a landmark moment for astronomy.
Oh, absolutely.
Telescopes pointed at the constellation Aquila, which is about 437 light years away, have captured the most detailed, structurally complex view we have ever seen of a new solar system forming.
It's stunning.
And the anchor of this whole system is a baby star. They named it WISPIT 2.
Right.
And surrounding it is this colossal disk of gas and dust. Embedded in that disk are two confirmed heavyweight planets, and they are actively gorging on material and carving out their orbits.
Which is just wild to see in real time.
It really is. So our objective today is to explore exactly how those chaotic clouds of dust actually transform into structured worlds. We're going to look at what these newly discovered giant baby planets look like, and how this 5 million-year-old star holds the secrets to our own 4.6 billion year history.
Yeah, the transition from theoretical modeling to direct observation, it really just cannot be overstated here.
Because it used to just be math on a chalkboard.
Exactly. For decades, the intricate mechanisms of planetary accretion, how microscopic dust grains overcome electrostatic barriers, how they stick together to grow into pebbles and then planetesimals and eventually into massive gas giants.
Wow.
All of that mostly lived in fluid dynamics equations and magnetohydrodynamic simulations.
Which is a mouthful.
It is.
Yeah.
But basically, we knew the math worked. The problem was ground truth verification was really scarce.
We could just go out and take a picture of it.
Right. But WISPIT 2 offers us this multi-planet laboratory where we can finally test those models against reality. We can measure the exact mass, the temperature, the orbital kinematics of these planets as they are actively being forged.
Okay, so let's start with the anchor of the whole thing, the star itself, WISPIT 2.
Okay.
It's characterized as a pre-main sequence star, and it's roughly 5 million years old. Now, to you and me, 5 million years sounds ancient.
Right, sure.
But against the 4.6 billion year age of our own sun, WISPIT 2 is basically a newborn.
Very much so.
But the metric that really caught my eye is its mass. It's clocked at 1.08 solar masses.
Yeah, that's the crucial number.
Because it makes it a near-perfect analog for what our sun looked like when it was a baby. It's essentially a twin.
Exactly. It's that 1.08 solar mass metric that makes it so valuable. Because its composition and size mirror our sun, the surrounding protoplanetary disk, that swirling reservoir of leftover gas and dust, is the perfect proxy for the primordial soup that built Earth.
Right. But you mentioned it's a pre-main sequence star, meaning it hasn't turned on yet.
Basically, yes. It hasn't achieved the internal pressure and temperature required to ignite sustained hydrogen fusion in its core.
So if WISPIT 2 hasn't turned on its core hydrogen fusion yet, where's the thermal budget coming from? Is the surrounding material colder? Or is the violence of gravity providing the heat? How is it generating enough energy to keep the disk from just freezing into solid ice?
That is a great question, and it goes straight to the thermodynamics of how stars are born.
Okay.
While WISPIT-2 lacks that sustained hydrogen fusion, it's driven by something we call the Kelvin-Helmholtz mechanism.
The Kelvin-Helmholtz mechanism. Got it. What is that?
So the star is still in the process of gravitational collapse. It formed from a vast, cold, molecular cloud, and as that immense volume of gas falls inward on itself, gravitational potential energy gets converted into kinetic energy.
Because it's moving faster.
Exactly. And as those gas particles compress and collide at higher and higher velocities, that kinetic energy is converted into thermal energy.
So it's essentially heating up because it's crushing itself.
That is exactly the mechanism. It's glowing purely from the intense friction and pressure of its own gravitational contraction.
Wow.
Yeah, and according to the virial theorem, about half of the gravitational potential energy released during this collapse radiates away as starlight.
And the other half?
The other half remains trapped inside, and it steadily raises the core temperature. Eventually, millions of years from now, that core temperature will hit roughly 15 million Kelvin.
Which is when it finally turns on.
Right. That's what's required to sustain hydrogen fusion, and WISPIT-2 will officially join the main sequence. But right now, the fact that it hasn't ignited fusion is huge.
Why is that so important for the planets?
Because it hasn't generated the intense, sustained stellar winds yet. That outward radiation pressure that eventually blows all the primordial planet-making material out of the system.
Oh, I see.
Yeah. So the protoplanetary disk around WISPIT-2 is still dense, it's rich, and it's undisturbed.
So it's prime real estate for building planets.
Exactly.
Now, I know this isn't the absolute first time we've caught a system in this phase. Back in 2018, there was the discovery of PDS-70.
Yes, a very famous system.
Right, it's about 370 light years away, and astronomers found 2 forming protoplanets there. That was the first proof that we could actually witness planetary birth.
Mm-hmm.
But when I was looking into this, it seems like PDS-70 is treated as a proof of concept, whereas WISPIT-2 is being treated as this comprehensive laboratory.
That's a very fair assessment.
I kind of think of PDS-70 as like finding a single blurry Polaroid of a baby.
Ha!
Whereas WISPIT-2 is like finding an entire high-definition home video with a wider cast of characters. But what specific data does WISPIT-2 provide that fundamentally elevates our understanding compared to PDS-70?
Well, PDS-70 was a watershed moment for sure. It gave us the first unambiguous, direct images of protoplanets PDS-70b and C sitting inside a transition disk.
Right.
We could measure their hydrogen alpha emission, which is basically a specific wavelength of light that acts as a direct tracer of hot hydrogen gas accreting onto the planets.
So it proved that planets were actually gathering material.
Yes, it proved the accretion models were fundamentally correct. However, PDS-70 had limitations when it came to visibility of the disk structure itself.
Like the environment around the planets.
Exactly. The gaps were there, but the extended, complex architecture wasn't as cleanly defined.
So it was essentially just a narrow window into the process.
Yes. WISPIT-2, by contrast, has an extraordinarily extended disk. It has multiple, highly distinct concentric rings and these deeply carved gaps that are clean enough to measure precise kinematic deviations.
Meaning we can see how things are moving.
We aren't just seeing the planets glowing. We can measure the exact velocity field of the gas flowing around them. We can map the surface density gradients of the dust.
Wow.
WISPIT-2 allows us to observe not just the existence of the planets, but the real-time fluid dynamics of the environment they are manipulating.
Okay, so let's talk about the planets doing the manipulating.
Mm-hmm.
Because the scale of these bodies is just staggering.
They are massive.
Right. The first one confirmed, WISPIT-2b, was directly imaged in 2025. This is a gas giant with a mass roughly 4.9 times that of Jupiter.
Mm-hmm.
And its orbital location is way out in the deep freeze of the system. It's sitting at a distance of 57 to 60 astronomical units from the host star.
Right.
And for context, for you listening, Neptune sits at 30 AU. So WISPIT-2b is orbiting at twice the distance of the furthest major planet in our own solar system.
Yeah, and a 4.9 Jupiter mass object at 60 AU poses a significant challenge to our standard formation models, which we can get into later.
Right, but physically, what is it doing out there?
Well, regarding its physical state, WISPIT-2b is currently operating as a massive gravitational sink.
Oh, hey.
At 60 AU, the orbital period is vast, meaning the planet takes hundreds of years to complete a single revolution around the star.
Just 1 year for that planet is centuries for us.
Exactly. And as it slowly plows through the outer disk, it is accreting gas and dust within its hill sphere.
That's hill sphere.
Yeah, the hill sphere is the region where the planet's gravity dominates over the gravitational pull of the host star.
Oh, I see. So anything that enters that sphere is basically getting sucked in.
Pretty much.
And that accretion process itself is generating a massive amount of infrared radiation, correct?
Yeah.
I mean, the heat isn't just coming from the star. It's coming from these colossal glowing babies hidden in the dust.
Yeah.
The material isn't just gently falling onto the planet. It's slamming into it.
Yes, the physics of accretion are incredibly violent.
How violent are we talking?
Well, gas falling toward the planet accelerates to supersonic speeds.
Wow.
And when it finally strikes the denser atmosphere, or the surface of the growing protoplanet, it creates an accretion shock.
Oh, man.
The kinetic energy of that infalling gas is instantaneously converted into heat. It raises the local temperature to thousands of degrees.
So even out in the deep freeze, it's scorching hot.
Exactly. That is why a planet out at 60 AU, a region where the ambient temperature of the disk is barely above absolute zero, is glowing brightly enough in the near-infrared spectrum to be detected 437 light-years away.
Because it's radiating its own formation heat.
Yes.
Okay, so that's the outer planet. But that brings us to the March 2026 data, which confirmed the second planet, WISPIT-2c.
Right.
And here's where it gets really interesting. The architecture of this system becomes highly counterintuitive.
It does.
WISPIT-2c orbits much closer to the star, at roughly 14 AU. Yet, it is estimated to be between 8 and 12 Jupiter masses. It is roughly twice as massive as the outer planet.
Yes, it's a heavyweight.
But confirming this required spectroscopic data, specifically looking for carbon monoxide. Walk me through the physics of that detection. Because finding something at 14 AU seems way harder than finding something at 60 AU.
It is significantly harder. Confirming WISPIT-2c was a huge triumph of high-resolution spectroscopy.
Why is it so difficult?
Because at 14 AU, the angular separation between the planet and the star is incredibly tight. The glare of WISPIT-2 is overwhelming.
It's just blinding the telescope.
Right. So to prove that this faint point of light wasn't just a background artifact or like a localized clump of hot dust, astronomers utilized integral field spectrographs.
Okay.
They needed to analyze the specific wavelengths of light being emitted. They targeted the K-band in the near-infrared. And specifically, they were looking for the rho vibrational absorption bands of carbon monoxide, which occur around 2.3 microns.
Wait, why carbon monoxide, though? Why not look for hydrogen or methane?
That's a good point. So carbon monoxide is an exceptionally stable molecule, and it's a dominant carbon-bearing species in the hot, high-pressure environments of forming gas giant atmospheres.
Oh, okay, so it survives the heat.
Exactly. Methane, on the other hand, requires much cooler temperatures to remain stable in large quantities.
And hydrogen.
Hydrogen is abundant, sure, but its emission lines can often be confused with stellar activity or just general accretion flows in the broader disk.
So it's not specific enough.
Right, but the specific rho vibrational signature of carbon monoxide acts as an unequivocal chemical fingerprint for a dense planetary mass atmosphere.
It's the smoking gun.
Exactly.
But finding the molecule isn't enough on its own, is it? I mean, you have to prove it actually belongs to something orbiting the star and not just gas floating around.
Yes, and that is where the kinematics come into play.
The movement.
Right. By observing the K-band spectrum with incredibly high spectral resolution, astronomers can measure the Doppler shift of those carbon monoxide lines.
Like how a siren sounds different when an ambulance drives past you.
Exactly like that, but with light. As the planet orbits the star, its velocity relative to our telescopes on Earth changes. When it moves slightly toward us in its orbit, the K-band lines blue shift.
And when it moves away.
They redshift. So by measuring this precise shift, astronomers can calculate the Keplerian velocity of the object.
The actual speed of its orbit.
Yes. And the data showed that this glowing source of carbon monoxide was moving at the exact velocity required for an object in a stable bound orbit at 14 AU.
So it couldn't just be random gas.
No, it was definitive proof of a massive 8 to 12 Jupiter mass planet.
Okay, I see the logic in the detection, but the mass distribution still seems completely backward to me.
How so?
Well, WISPIT-2c is at 14 AU. WISPIT-2b is at 60 AU. The circumference of an orbit at 60 AU is vastly larger, right?
Yes, it is.
So the outer planet has a much longer track to run, meaning it has a much wider volume of space to sweep through. Given that, why is the inner baby so much hungrier? Shouldn't the planet further out have more room to sweep up material and get bigger?
I get why you'd think that. It's a very common misconception to equate orbital circumference with available mass.
Oh, really?
Yeah. In a protoplanetary disk, we have to look at the radial surface density profile. The material, the gas and the dust is not distributed evenly.
It's not just a flat, uniform sheet.
Right. The disk is governed by fluid dynamics. And typically, the surface density is highest near the star and falls off exponentially as you move outward.
So the raw material is just thicker on the inside track.
Thicker by orders of magnitude.
Wow.
To use a mechanical analogy, imagine driving a snowplow.
All right.
The outer planet at 60 AU is driving a massive, sweeping route across a giant parking lot. But the parking lot only has a sparse half-inch dusting of snow.
Right.
The inner planet at 14 AU has a much shorter route, but it is driving through drifts that are 10 feet high.
Okay. That makes perfect sense. That tracks completely. But is it just a static distribution of density, or is material actively moving toward the inner planet?
It is highly dynamic. We have to consider radial drift, particularly for the pebble-sized solid particles in the disk.
Radial drift, so things are migrating.
Yes. In the disk, the gas is partially supported by outward thermal pressure, meaning the gas actually orbits slightly slower than the Keplerian velocity.
Slower than a purely gravitational orbit.
Right. But the solid pebbles, they don't feel that gas pressure. They want to orbit at the faster, full Keplerian velocity.
Wait, so the pebbles are trying to go fast, but the gas is going slow.
Exactly.
Meaning the pebbles are constantly fighting a headwind from the slower moving gas.
That's the perfect way to visualize it. And that headwind acts as aerodynamic drag.
Oh, okay.
It bleeds orbital angular momentum from the pebbles, which causes them to constantly spiral inward toward the star.
Oh, wow.
So not only is WISPIT 2c sitting in an inherently denser region of the disk to begin with, it is positioned in a cosmic bottleneck.
The bottleneck.
Right? Where vast quantities of solid material from the outer disk are continually drifting inward, delivering an endless supply of mass right to the inner planet's feeding zone.
So it's basically sitting at the end of a buffet line.
Exactly. WISPIT 2c is gorging itself on this inward migration, and that allows it to rapidly balloon to 10 times Jupiter's mass.
While the outer planet is starving.
Well, WISPIT 2b is forced to accrete from the much sparser depleted material out in the outer disk, so yes, it grows much slower.
That aerodynamic drag mechanism completely changes how I view the disk. It's not a static ring. It's a conveyor belt.
It absolutely is.
And the planets are actively disrupting that conveyor belt. Which naturally brings us to the visual architecture of the WISPIT 2 disk. We talked about how we're seeing these visible scars these planets are leaving behind. We see these massive, bright, concentric rings of dust separated by deep, dark gaps.
Right.
If we picture a giant vinyl record, the dust makes up the ridges, and the planets are the needles carving out the grooves, pulling in mass as gravity takes over. But how exactly does a planet's gravity physically clear a gap that is billions of miles wide? I mean, it can't possibly accrete all that material, can it?
Oh, no, it doesn't accrete all of it. In fact, it accretes a relatively small fraction.
So where does the rest of it go?
The vast majority of the material is pushed away through gravitational torques.
Torque?
Yes. When a massive planet like WISPIT 2b or 2c orbits within a gaseous disk, it interacts gravitationally with the surrounding material, and it launches spiral density waves.
The spiral density waves, that sounds intense.
They are. These waves are very similar to the wake created by a boat moving through water. As these density waves propagate away from the planet, both inward toward the star and outward into the deeper disk, they eventually shock the gas.
They shock it, meaning they compress it and transfer momentum.
Yes. The waves deposit angular momentum into the outer disk, which physically pushes the gas further away from the star.
Oh, okay.
And conversely, they extract angular momentum from the inner disk, causing that gas to fall closer to the star.
This is pushing material in both directions away from its orbit.
Exactly. The net result is that the gas is actively repelled from the planet's orbit, creating a cleared region or a gap.
But the images we are seeing from the telescopes are primarily showing dust, not just gas, right?
Correct.
So how does pushing the gas away create those incredibly sharp, bright rings of dust on either side of the gap?
This ties directly back to the aerodynamic drag we just discussed.
The headwinds.
Right. When the planet pushes the gas away and creates a gap, it creates a localized pressure gradient at the edge of that gap.
Meaning the gas pressure spikes.
Yes. The gas pressure increases sharply just outside the cleared zone. Now, remember that solid pebbles drift inward due to the gas headwind.
Right, they're spiraling in.
But when those inward drifting pebbles hit that sudden spike in gas pressure at the outer edge of the gap, the headwind disappears.
Oh.
The pressure bump acts as an aerodynamic trap.
So they just stop.
The pebbles stop drifting inward and they pile up massively at the edge of the gap.
So the planet is essentially building a dam.
It is building a dam.
Yeah.
And the bright rings we see in the telescope images are the reservoirs of dust trapped behind that dam.
That is incredible.
The gap itself is largely cleared of both gas and millimeter-sized dust, making it look dark, while the edges glow brilliantly because of the concentrated dust accumulation.
Okay, let me stop you there, though, if I'm playing devil's advocate here.
Okay.
How do we know for sure that a dark gap equals a planet? Couldn't a gap be caused by something else?
Like what?
Well, what if it's a snow line? Like a region where a specific gas, like carbon monoxide, suddenly freezes into a solid, changing the opacity of the disk and just making it look like a gap. Or what about magnetic dead zones where turbulence drops off?
That is a crucial distinction. And honestly, it's a major debate in planetary science.
All right.
For years, when we only had lower resolution imagery, alternative theories like snow lines or magnetorotational instability variations were highly viable explanations for disk gaps.
Because we couldn't prove otherwise.
Exactly. However, WISPIT 2 provides the kinematic data to rule those out.
How?
Well, a snow line changes the chemical state of the disk, but it does not drastically alter the velocity of the gas flow. A massive planet, however, does.
Ah, okay.
By using high-resolution spectroscopy, astronomers mapped the Keplerian velocity of the carbon monoxide gas inside and around the gaps, and they found localized, distinct deviations in the gas velocity, tiny twists or kinks in the kinematic map.
Like the gas is swerving.
Yes.
So the gas is literally flowing around the gravitational well of the planet.
Precisely. Those kinematic twists are the undeniable dynamic signatures of a massive, localized gravitational body. They prove we aren't just looking at a chemical illusion or a shadow.
We are looking at the gravitational fingerprint of a planet.
Exactly. We don't necessarily have to see the planet to know it's there. Gravity leaves a fingerprint. And this fingerprint analysis is leading to even more discoveries in the WISPIT 2 system.
Really? There's more?
Oh, yeah. Beyond the massive gaps carved by 2b and 2c, researchers have identified a third, much narrower and shallower gap further out in the disk.
And the assumption is that this is a third planet, just smaller.
Exactly. The depth and width of a gap are directly proportional to the mass of the planet carving it, balanced against the viscosity of the disk trying to refill it.
So what does the math say about this third one?
The math suggests this third gap is being maintained by a planet roughly the mass of Saturn.
A Saturn-sized baby.
Right. It is currently too low mass and therefore not generating enough accretion heat to be directly imaged by our current instruments.
But the fingerprint is there.
The dynamic signature is there. As Chloe Lawler, she's a PhD student at the University of Galway, she pointed out that this multi-gap architecture strongly implies an entire planetary system is sequentially forming. The structure itself is a historical ledger of the system's evolution. She said it's basically the best look into our own past that we have to date.
That is just wild to think about. And it leads perfectly into the technological reality of this discovery. I mean, I marvel at the fact that we can see a fingerprint 437 light years away. We are analyzing the kinematic twists in gas flows and the thermal radiation of planetary accretion, all while fighting the blinding glare of the host star.
It's a monumental engineering feat.
The analogy I usually hear for this is trying to photograph a single firefly sitting next to a lighthouse from thousands of miles away.
That's the classic one, yeah.
But given the physics of the K-band infrared and the adaptive optics involved, I feel like a better analogy is trying to detect the specific thermal signature of a single lit match sitting on the rim of an industrial blast furnace from 30 miles away through a torrential downpour.
Huh! That is remarkably accurate.
Right. So how are the telescopes physically filtering out the blast furnace to see the match? Break down the paparazzi gear for us.
Okay, well, the torrential downpour in your analogy represents Earth's atmosphere.
Okay.
Even on the highest, driest peaks of the Atacama Desert in Chile, where the European Southern Observatory's very large telescope, the VLT, is located, the atmosphere is turbulent.
The air is always moving.
Right. Packets of air at varying temperatures act like thousands of tiny moving lenses. They are continuously refracting and distorting the incoming starlight.
Which is why stars twinkle.
Exactly.
Huh?
If you take a standard long exposure photograph, that turbulence smears the light of the star into a massive fuzzy halo that completely engulfs any faint planets.
So the first step is basically removing the atmosphere. How does the VLT achieve that without actually going into space?
Through advanced adaptive optics, primarily using an instrument called SPHERE.
SPHERE, what does that do?
SPHERE relies on a Shack-Hartman wavefront sensor and a deformable mirror.
The deformable mirror, like it changes shape.
Yes, literally. The telescope analyzes the incoming light from WISPIT-2. The wavefront sensor splits the telescope's pupil into thousands of subapertures, and it measures exactly how the wavefront of the light has been warped by the atmosphere at that exact microsecond.
So it takes a reading of the distortion.
Right. And then it mechanically corrects it in real time.
How fast is real time?
It sends that data to a computer, which calculates the inverse of that distortion. The computer then sends electrical signals to thousands of microscopic actuators located behind a thin, flexible mirror.
Wow.
Those actuators push and pull the mirror, physically deforming its shape to exactly cancel out the atmospheric turbulence. And it does this at a frequency of over 1,000 times per second.
1,000 times a second. That's unbelievable.
It's incredible technology. It essentially flattens the wavefront, effectively removing the Earth's atmosphere and turning the blurry halo back into a sharp, single point of starlight.
Okay, but the star is still a blast furnace.
Yeah.
I mean, you have a sharp point of light now, but it's still millions of times brighter than the planet. How do you block it?
Once the light is corrected by the adaptive optics, it is fed into a coronagraph.
A coronagraph.
Right. At its most basic level, a coronagraph is a highly engineered physical mask placed exactly at the focal plane of the telescope. It functions as an artificial eclipse, physically blocking the core light of the star.
Oh, clever. So you just put a dot over the bright part?
Basically, yes. However, because light acts as a wave, simply blocking the center isn't enough. The starlight diffracts. It bends around the edges of the mask and creates bright concentric rings that would still blind the sensors.
So the light leaks around the edge?
Exactly. But modern coronagraphs, like the Apodice pupil Liat coronagraphs used on SPHERE, utilize secondary masks and complex optical shapes to actively suppress those diffraction rings.
Oh, wow.
This allows the faint infrared glow of the disk and the outer planet, WISPIT-2b, to finally emerge from the darkness.
Okay, so that covers SPHERE and the discovery of the outer planet. But WISPIT-2c is at 14 AU. It's incredibly close to the star.
A coronagraph alone isn't enough to resolve something that tight, is it?
No, it is not. At 14 AU, the angular separation is below the diffraction limit of a single 8-meter mirror on the VLT.
Meaning the mirror just isn't big enough to see it.
Exactly. The resolving power of a telescope is fundamentally limited by the diameter of its primary mirror. To see something as tight as WISPIT-2c, you would need a mirror over 100 meters wide, which of course doesn't exist.
So what did they do?
This is where the technological leap of the VLTI, the Very Large Telescope Interferometer, and the Gravity Plus instrument becomes the hero of the story.
Interferometry, that's essentially combining multiple telescopes to act as one giant one, right?
But how do you combine the light without losing the phase data? I imagine it's super delicate.
That is the supreme engineering challenge. The VLTI takes the light collected from all 4 of the 8-meter unit telescopes on the mountain.
Okay.
By combining that light, they synthesize a virtual telescope with an effective baseline or diameter of up to 130 meters.
Wow, that solves the size problem.
It does. But to make that work, the light waves from each telescope must arrive at the central Gravity Plus instrument at the exact same time, down to a fraction of a wavelength of light.
But wait, the telescopes are physically located in different places on the mountain. The light traveling from the star hits telescope A slightly before it hits telescope B.
Exactly. There is an optical path difference.
So how do you fix that?
To correct this, the light from each telescope is routed into subterranean tunnels equipped with delay line.
Delay line.
Yes. These are essentially highly precise mirrors mounted on carriages that physically move back and forth along rails to artificially lengthen or shorten the path the light travels.
Wait, they have carts on rails, underground moving mirrors to catch the light.
Literally, yes. They continuously adjust, compensating for the rotation of the Earth, ensuring that the light waves from all 4 telescopes align perfectly when they are combined.
That sounds like science fiction.
It's brilliant engineering, and the recent Gravity Plus upgrade was specifically what pushed this over the edge to find WISPIT-2c.
So without that upgrade, we wouldn't have seen it.
Without that upgrade, the inner planet would have remained entirely hidden by the star's overwhelming light. The upgrade vastly improved the fringe tracking capabilities. That's the system that actively locks onto the phase of the combined light waves, and it integrated new, more powerful adaptive optics directly into the array.
Amazing.
It allowed gravity plus to suppress the starlight and increase contrast at incredibly tight angular separations, revealing WISPIT 2C in the K-band spectrum.
Okay, so now that we understand what we're seeing and how we're seeing it, what does this actually change for the future of science? We have the mass, we have the orbits, we have the spectroscopy, and the instrumentation. Now we have to contextualize this.
Right.
We have a 4.9 Jupiter mass planet at 60 AU and a roughly 10 Jupiter mass planet at 14 AU, all forming in a system that is only 5 million years old. How does this architecture challenge the existing models of planetary evolution? Because from what I read, the timeline here is causing a major headache for the standard core accretion model.
Oh, it is causing a profound reevaluation of the math.
Let's get into it.
Okay, so in the standard model of gas giant formation, known as core accretion, a planet must first build a solid core.
Right.
Microscopic dust grains in the disk collide and stick through electrostatic forces, growing into pebbles. These pebbles then undergo streaming instabilities, clumping together to form kilometer-sized planetesimals.
Basically building blocks.
Yes. These planetesimals collide and merge in a process called oligarchic growth until they form a rocky, icy core roughly 10 times the mass of Earth.
And once it hits that 10 Earth mass threshold, what happens?
Well, at that point, the gravity is strong enough to trigger runaway gas accretion. It starts pulling in the hydrogen and helium to become a Jupiter.
But you said there's a problem with the timeline.
Yes. The rate at which planetesimals collide and grow depends heavily on their orbital velocity and the density of material. Close to the star, orbital periods are short and density is high, so a core can build relatively quickly.
Makes sense.
But at 60 AU, where WISPIT 2b is located, the orbital periods are centuries long and the solid material is sparse.
Right.
Standard core accretion models suggest it should take tens of millions of years to build a 10 Earth mass core at 60 AU. But WISPIT 2 is only 5 million years old.
And WISPIT 2b is already a fully formed 5 Jupiter mass giant.
Exactly.
So the timeline doesn't work. The planet is too big, it's too far out, and it's too young. Does that mean the alternative theory, disk instability, is the answer?
Well, disk instability posits a completely different top-down mechanism. It argues that if a protoplanetary disk is massive enough and cold enough, the gravity of the gas itself overwhelms the thermal pressure, keeping it stable.
Okay, so the gas just collapses on itself.
Yep, exactly. Portions of the disk fragment and collapse in on themselves directly. It rapidly forms massive gas giants without ever needing to build a solid core first.
And is that fast enough?
Yes, this process can happen in a few thousand years, easily satisfying the 5 million year age limit of WISPIT 2.
Wow, okay. But there's a catch with disk instability too, isn't there?
Always a catch. The catch is thermodynamics.
Of course it is.
For a clump of gas to collapse under its own gravity, it must be able to cool rapidly.
Why?
Because as it collapses, it heats up, increasing thermal pressure, which causes the clump to bounce back and dissipate. It can only permanently collapse if the cooling time is shorter than the dynamic timescale of the collapse.
So it has to cool off faster than it heats up.
Exactly. Now, at 60 AU, the disk is cold and optically thin enough to cool efficiently, making disk instability a highly viable mechanism for WISPIT 2b.
Let me guess. At 14 AU, where WISPIT 2c lives, it's too hot to cool efficiently.
You nailed it. At 14 AU, the disk is optically thick and much warmer. The cooling times are generally too long for disk instability to function. A clump would heat up and expand before it could ever form a planet.
So wait, WISPIT 2c sits too close for disk instability, but WISPIT 2b sits too far for standard core accretion.
Yes.
The system is defying both models simultaneously.
Which is precisely why co-author Christian Ginsky described WISPIT 2 as a critical laboratory for the entire planetary system. It's forcing us to rethink everything.
So how are they reconciling this? What's the leading hypothesis?
The current leading hypothesis to reconcile this is an accelerated version of core accretion, driven by the aerodynamic drag we discussed earlier.
Oh, pebble accretion.
The headwind thing again. Exactly. If the 10 Earth mass core isn't built by slowly crashing massive planetesimals together, but instead by sweeping up millions of millimeter-sized pebbles that are constantly drifting inward, the growth rate skyrockets.
Oh, because it's just gobbling up a steady stream of food.
Right. Pebble accretion bypasses the traditional timescale bottlenecks. It potentially allows a core to form at 60 AU within a million years, triggering the gas runaway fast enough to explain WISPIT 2b.
That is just incredible.
And if we connect this to the bigger picture, moving from one anomaly like PDS 70 to now having multiple systems proves this is a common cosmic process. We are actively building a catalog of birth sites.
And we have even better tools coming online soon, don't we?
Oh, absolutely. WISPIT 2 is now a prime target for the James Webb Space Telescope to probe the disk chemistry and atmospheres. And the upcoming extremely large telescope might even be able to image that suspected third planet.
I can't wait to see those images. But I have to ask about planetary migration. So what does this all mean for the layout? We have these two massive bowling balls orbiting in the disk. Once the gas fully dissipates and the disk is gone, are they going to stay put in these orbits of 14 and 60 AU? Or will they act like cosmic bowling balls migrating inward and disrupting the formation of other worlds?
Migration is almost a certainty. The current orbits are heavily influenced by the mass of the gas disk. Because WISPIT 2b and 2c are massive enough to carve deep gaps, they enter what is known as Type 2 migration.
What does that mean?
It means they become gravitationally locked to the viscous evolution of the disk itself. As the disk slowly accretes onto the star over millions of years, the planets will be dragged inward with it.
So WISPIT 2c could migrate from 14 AU down to 5 AU, or even become a hot Jupiter skimming the surface of the star.
It is entirely possible. Furthermore, once the gas dissipates, the dampening effect it has on the planet's eccentricities disappears.
Meaning their orbits could get wild.
Yes. If WISPIT 2b and 2c end up in a gravitational resonance where their orbital periods align in a simple integer ratio, the gravitational perturbations will amplify. This can lead to chaotic scattering.
What happens during chaotic scattering?
Well, one planet could be flung into a highly elliptical orbit while the other is ejected from the system entirely.
Just thrown out into deep space.
Exactly. And this kind of violent orbital reshuffling is exactly what we believe happened in our own solar system during the Grand Tack and the NICE model scenarios, where Jupiter and Saturn migrated inward and then outward, scattering rocky material and icy comets throughout the inner solar system.
Fundamentally shaping the environment that allowed Earth to form.
Exactly.
That is the perfect connection to make as we synthesize this entire discussion. The monumental effort required to map the K-band spectroscopy of WISPIT 2c, to utilize the delay lines of the VLTI underground tunnels, and to actively deform mirrors thousands of times a second to cancel the atmosphere. All of it serves a singular purpose.
It really does.
When we look at WISPIT 2, we aren't just looking at random gas giants in Aquila. We're not just cataloging abstract physics. We're looking into a 5-million-year-old mirror reflecting the chaotic, highly complex, and violent 4.6-billion-year-old origin story of the very ground we stand on.
We are watching the raw materials of existence organize themselves.
Exactly.
And, the most profound aspect of that mirror is what we currently cannot see.
What do you mean?
Well, with all of our adaptive optics, the coronagraphs, and the interferometry, we are only capable of resolving the outer, massive gas giants. The 5 and 10 Jupiter mass Titans sitting way out at 14 and 60 AU.
Right.
But the region within 5 AU of the star, the terrestrial planet formation zone, equivalent to where Earth, Venus, and Mars sit in our system that remains hidden.
Behind the glare of the young star.
Yes, and behind the thickest, most optically dense regions of the inner disk. Within that unseen inner crucible, tiny grains of silicate dust and iron might be quietly colliding right now.
Oh, well.
As we observe the majestic orbital dance of those outer gas giants, we have to acknowledge that hidden deep within the blinding light, the microscopic foundations of a rocky, potentially habitable Earth-like world might be violently forging itself, just patiently waiting for the dust to clear.
It is a truly remarkable realization. The fact that we have the technological capacity to observe a solar system taking its first breath and the theoretical frameworks to understand the mechanics driving it is a testament to the golden age of astronomy we're currently living in.
It really is an exciting time for the field.
Thank you for joining us on this rigorous exploration of WISPIT 2 and the mechanics of planetary genesis. Keep looking up and keep questioning the universe around you.